Contactor point burn and melting can stem from several issues. Firstly, a circuit breaker trip can indeed be a cause. When a circuit breaker trips, it can create a high current arc between the contactor points. This arc generates intense heat, which can damage the points, leading to burning or even melting. Secondly, misalignment of the contactor points is another potential cause. When the points are not properly aligned, they may not make complete and uniform contact. This incomplete contact increases resistance and causes arcing and overheating at the point of contact, eventually resulting in the points burning or melting. Thirdly, dirty contacts are a common culprit. Environmental factors such as dust, dirt, moisture, and other contaminants can accumulate on the contactor points. These contaminants reduce the conductivity of the points and increase resistance. The increased resistance leads to arcing and heat buildup, damaging the contact surfaces. Beyond these, there are other possible causes to consider. One is excessive current. If the current flowing through the contactor consistently exceeds its rated capacity, the points will overheat. This overheating can quickly lead to burning and melting of the contactor points. Another is overvoltage. If the voltage applied to the contactor is too high, it can cause excessive arcing between the points. This arcing generates heat that damages the points, potentially causing them to burn or melt. Mechanical wear is yet another factor. Over time, the contactor points experience wear and tear from repeated operation. This wear can lead to a loss of contact pressure and increased resistance. As resistance increases, so does heat, eventually damaging the points. Finally, improper installation can be a contributing factor. If the contactor is not installed or wired correctly, it can create conditions that lead to arcing and subsequent point damage. It is important to identify the root cause of the contactor point burn or melting to prevent it from happening again. A thorough inspection of the contactor, the circuit breaker feeding the motor, and all associated wiring is necessary to diagnose the problem. This inspection should include checking the contactor points for signs of wear, damage, or contamination. Also, verify the proper alignment of the points and ensure that the contactor is securely mounted. Further, the circuit breaker should be tested to verify that it is functioning correctly and that it is properly sized for the motor it is protecting. Finally, inspect the wiring for any signs of damage, loose connections, or corrosion. To elaborate on the causes of contactor failure, let's delve into each factor with more technical detail. Starting with circuit breaker trips, understanding the nature of the arc is crucial. When a circuit breaker interrupts a fault current, it doesn't happen instantaneously. There is a brief period where the current is rapidly decreasing, but is still substantial. During this time, a high current arc is generated between the separating contacts of the circuit breaker. This arc is essentially a plasma discharge with extremely high temperatures. If the circuit breaker is located very close to the contactor, or if the wiring between them is undersized, a portion of this arc energy can propagate to the contactor points. The intense heat from the arc can cause localized melting and burning on the contactor surfaces. Moving on to misalignment, the pressure with which the contacts mate is designed to meet specific requirements. A misaligned contactor will have reduced contact surface area, which results in high heat. This excessive heat can cause the silver plating on the contacts to melt or vaporize, leading to contact degradation and eventually failure. With regards to dirty contacts, the increased resistance due to contamination can be substantial. Even a thin layer of dust or corrosion can significantly impede current flow. This increased resistance generates heat according to Joule's law, which states that the heat generated is proportional to the square of the current times the resistance, or I squared R. The higher the resistance, the more heat is generated for the same amount of current. Over time, this heat can cause the contactor material to degrade, leading to burning and melting. When considering excessive current, it is important to differentiate between short-term overloads and sustained overcurrent conditions. Short-term overloads, such as those experienced during motor starting, are typically tolerated by the contactor for a short duration. However, a sustained overcurrent condition, where the current exceeds the contactor's continuous current rating for an extended period, will cause the contactor points to overheat. The heat generated can exceed the melting point of the contactor material, resulting in permanent damage. Overvoltage can cause a phenomenon known as dielectric breakdown. The air gap between the open contactor points is designed to withstand a certain voltage level. If the voltage exceeds this level, the air can become ionized, creating a conductive path for current to flow. This results in an arc, which, as previously discussed, can cause significant damage. Moreover, transient overvoltage conditions, such as voltage spikes caused by lightning strikes or switching surges, can also damage the insulation within the contactor, leading to insulation breakdown and eventual failure. With mechanical wear, the constant making and breaking of the contacts will eventually cause erosion of the contact surfaces. Each time the contactor opens or closes, a small amount of material is transferred from one contact to the other. Over time, this material transfer can lead to pitting, roughness, and uneven contact surfaces. These imperfections reduce the contact area and increase resistance, which in turn leads to overheating and potential failure. Finally, when looking at improper installation, it is critical that the contactor is properly sized for the application. Using an undersized contactor can lead to overheating and premature failure. Additionally, proper wiring practices are essential. Loose connections, undersized wires, or incorrect wiring can create excessive resistance and heat. The contactor should also be mounted in a well-ventilated location to allow for adequate heat dissipation. Furthermore, the contactor should be protected from moisture, dust, and other contaminants. It is also necessary to use appropriate torque to tightening the terminal connections according to the manufacturer's instructions. Under-tightening can cause loose connections and over-tightening can damage the terminals. When performing a thorough inspection of a contactor, several key areas should be examined. Firstly, the contact surfaces should be visually inspected for any signs of wear, pitting, erosion, or discoloration. A magnifying glass can be helpful for detecting fine details. The contact resistance should be measured using a microometer. A high contact resistance indicates that the contacts are not making good contact, which could be due to contamination, wear, or misalignment. The contactor should be operated manually to check for smooth and free movement. Any binding or sticking could indicate a mechanical problem. The coil voltage should be measured to ensure that it is within the specified range. An incorrect coil voltage can cause the contactor to operate erratically or not at all. The insulation resistance should be measured using a megometer. A low insulation resistance indicates that the insulation is breaking down, which could lead to electrical shock or equipment damage. The wiring connections should be inspected for tightness and corrosion. Loose or corroded connections can cause excessive resistance and heat. The enclosure should be inspected for any signs of damage or deterioration. Cracks or holes in the enclosure can allow moisture and contaminants to enter, which could damage the contactor. The ambient temperature should be checked to ensure that it is within the contactor's operating range. Excessive heat can shorten the life of the contactor. Vibration can also damage the contactor. Excessive vibration can cause the contacts to bounce, which can lead to arcing and wear. It can also loosen wiring connections and damage the enclosure. Chemical exposure can also damage the contactor. Exposure to corrosive chemicals can cause the contacts to corrode and the insulation to break down. Altitude can also affect the performance of the contactor. At higher altitudes, the air is thinner, which reduces the cooling effect of convection. This can cause the contactor to overheat. The inrush current of the motor should be considered when selecting a contactor. The contactor must be able to withstand the high inrush current that occurs when the motor starts. The duty cycle of the motor should also be considered. A motor that operates frequently will require a more robust contactor than a motor that operates infrequently. The National Electrical Code, NEC, provides guidelines for selecting and installing contactors. Adhering to these guidelines will help to ensure safe and reliable operation. NEC Article 430 covers motors, motor circuits, and controllers. NEC Section 430.83 specifies the horsepower ratings for contactors used to control motors. NEC Section 430.84 specifies the ampacity of the conductors used to connect the contactor to the motor. NEC Section 430.109 specifies the disconnecting means for motor circuits. When replacing a contactor, it is important to select a replacement that is equivalent to or better than the original. The replacement contactor should have the same voltage rating, current rating, and horsepower rating as the original. It should also have the same number of poles and the same type of contacts. In addition to these factors, the replacement contactor should also be compatible with the existing wiring and mounting hardware. It is also important to follow the manufacturer's instructions when installing the replacement contactor. Improper installation can damage the contactor and create a safety hazard. Regular maintenance can help to extend the life of a contactor. This maintenance should include periodically inspecting the contactor for signs of wear, damage, or contamination. The contactor should also be cleaned regularly to remove any dust, dirt, or debris. The wiring connections should be checked for tightness and corrosion. If any problems are found, they should be corrected immediately. Contactor failures can often be diagnosed by carefully examining the contactor and its associated wiring. A visual inspection can reveal signs of wear, damage, or contamination. Electrical testing can be used to measure the contact resistance, coil voltage, and insulation resistance. By carefully analyzing the symptoms and performing appropriate tests, it is often possible to identify the root cause of the failure and take corrective action. The size of the motor being controlled by the contactor has a direct impact on the current it draws. Larger motors require larger contactors with higher current ratings. If the motor is drawing more current than the contactor is rated for, it will overload the contactor and cause it to overheat. Variable frequency drives, VFDs, can introduce harmonic currents into the electrical system. These harmonic currents can cause additional heating in the contactor and shorten its lifespan. Surge suppressors can be used to protect contactors from voltage transients. Voltage transients can damage the contactor's insulation and cause it to fail. Proper grounding is essential for preventing electrical shock and equipment damage. The contactor should be properly grounded according to the NEC. The type of load being controlled by the contactor can also affect its lifespan. Inductive loads, such as motors and transformers, can generate voltage transients that can damage the contactor. Resistive loads, such as heaters and lighting, are less likely to cause voltage transients. The ambient temperature around the contactor should be considered when selecting a contactor. Contactors are typically rated for a maximum ambient temperature. Operating a contactor at temperatures above its rated maximum can shorten its lifespan. The humidity level around the contactor should also be considered. High humidity can cause corrosion and reduce the insulation resistance of the contactor. The altitude at which the contactor is operating can affect its performance. At higher altitudes, the air is thinner, which reduces the cooling effect of convection. This can cause the contactor to overheat. The presence of corrosive chemicals in the environment can also damage the contactor. Corrosive chemicals can cause the contacts to corrode and the insulation to break down. The amount of vibration in the environment can also affect the lifespan of the contactor. Excessive vibration can cause the contacts to bounce, which can lead to arcing and wear. The frequency of switching can also affect the lifespan of the contactor. Contactors that are switched frequently will wear out faster than contactors that are switched infrequently. The control voltage applied to the contactor coil must be within the specified range. Applying a voltage outside of this range can damage the coil and cause the contactor to fail. The contacts of the contactor must be properly aligned. Misaligned contacts can cause arcing and overheating. The contacts of the contactor must be clean and free of corrosion. Dirty or corroded contacts can cause increased resistance and overheating. The contactor must be properly sized for the application. An undersized contactor will overheat and fail prematurely. The contactor must be properly installed according to the manufacturer's instructions. Improper installation can damage the contactor and create a safety hazard. Regular maintenance is essential for extending the lifespan of a contactor. This maintenance should include inspecting the contactor for signs of wear, damage, or contamination. The contactor should also be cleaned regularly to remove any dust, dirt, or debris. The wiring connections should be checked for tightness and corrosion. If any problems are found, they should be corrected immediately. Some contactors are equipped with auxiliary contacts. Auxiliary contacts are used to provide additional control functions such as interlocking and status indication. The auxiliary contact should also be inspected and maintained regularly. The contactor should be replaced if it shows signs of excessive wear, damage, or contamination. Replacing a contactor before it fails can prevent costly downtime and equipment damage. When replacing a contactor, it is important to select a replacement that is equivalent to or better than the original. The replacement contactor should have the same voltage rating, current rating, and horsepower rating as the original. It should also have the same number of poles and the same type of contacts. In addition to these factors, the replacement contactor should also be compatible with the existing wiring and mounting hardware. It is also important to follow the manufacturer's instructions when installing the replacement contactor. Electrical arcing causes erosion of the contact surfaces. This erosion increases the contact resistance and can lead to overheating and failure. High inrush currents, especially during motor starting, can cause significant stress on the contactor. These high currents can cause the contacts to bounce and arc, which can damage the contact surfaces. Sustained overloads can cause the contactor to overheat. This overheating can damage the insulation and other components of the contactor. Voltage sags and surges can also damage the contactor. Voltage sags can cause the contactor to drop out, while voltage surges can damage the insulation. Harmonics can cause additional heating in the contactor. These harmonics can be generated by nonlinear loads, such as variable frequency drives and electronic power supplies. Radio frequency interference (RFI) can also interfere with the operation of the contactor. RFI can cause the contactor to operate erratically or not at all. Transient voltage suppressors (TVSs) can be used to protect contactors from voltage transients. TVS are designed to clamp the voltage to a safe level, preventing damage to the contactor. Ferrite beads can be used to suppress RFI. Ferrite beads are small, cylindrical components that are placed on the wiring to filter out RFI. Shielded cables can also be used to reduce RFI. Shielded cables have a metallic braid or foil that surrounds the conductors, blocking RFI. Proper grounding is essential for minimizing RFI. A contactor should be properly grounded to provide a low impedance path for RFI to ground. Line reactors can be used to reduce harmonics. Line reactors are inductive devices that are placed in series with the load to filter out harmonics. Capacitors can also be used to reduce harmonics. Capacitors are capacitive devices that are placed in parallel with the load to filter out harmonics. Active harmonic filters can be used to eliminate harmonics. Active harmonic filters are electronic devices that generate harmonic currents that are equal in magnitude and opposite in phase to the harmonic currents generated by the load. This cancels out the harmonic currents and reduces the total harmonic distortion. Regular inspections can help to identify potential problems before they lead to failure. These inspections should include a visual inspection of the contactor as well as electrical testing. A qualified electrician should perform these inspections. Proper maintenance can help to extend the life of the contactor and prevent costly downtime. This maintenance should include cleaning the contactor, tightening the wiring connections, and replacing any worn or damaged components. Following the manufacturer's recommendations for maintenance is essential. The manufacturer's recommendations provide specific instructions for maintaining the contactor, which can help to ensure that it operates reliably and safely.